You're going to learn something today. I'm not here on Drug Awareness Week to talk about just say no. You've all heard that sermon. What we want to learn about this science is we're going to talk about the neurobiology, what's going on in the brain when we use substances of abuse. Why are they called substances of abuse? Everything that is a substance of abuse is by definition landing in a certain pathway in your brain. Okay, so my name is Barbara Veit, and I am a molecular biologist. Hi, I'm the West Coast director of Truth Pharm. We are an organization that focuses on substance use and substance use disorder, also known as addiction. And our goal is to save lives and reduce harm caused by that. And what I do here, we're based on the East Coast. What I do here on the West Coast is I primarily educate. Okay, so that's what I'm going to do today. So I've broken this talk into kind of two specific sections: why and how substances of abuse affect the brain. What is going on inside that they affect the brain? And then who is at risk for developing the disease of addiction? And just by way of a show of hands, how many people in here think that like addiction is a disease that is primarily an adult concern? How many people think it's a concern for teens? Okay, good. And you guys have been learning stuff, okay? Now, we're going to learn the science behind that, okay? We're going to talk about the science behind that, because only by having information can you make better choices. Now, I want to introduce you to somebody. She was a student here at Miraleste a number of years ago. You will all be exposed at some time or another to substances of abuse. Remember, biology could care less if a substance is legal, illegal, whether you acquired it legally or illegally. Biology does not care. Okay? So, you're going to get exposed, and if you're an athlete, like a football player or a wrestler, you're probably going to maybe get a bad injury. At least you're more likely than somebody in band to get an injury that might require surgery and then pain medication afterwards. And you also have another time in your teen life where you may be exposed to an opioid or another substance, narcotic pain killer, and that would be when you get your wisdom teeth pulled. And so I want you to see, Katie's a very good example. She's going to describe what happened to her when she got her wisdom teeth pulled. She was a student here.
I grew up in Palos Verdes and I played a lot of sports. I was in a lot of like AP classes and stuff like that. I started off going to PV high school because it was more athletic oriented. I played soccer, so I wanted to go there. But I transferred to Peninsula High School, which is like the other school in PV. Yeah, I took. That's when I took like all my AP classes and stuff. And I played soccer, volleyball. I played a bunch of sports. So the first time I ever took one, I think I got my wisdom teeth pulled. And my mom like monitored them with me or whatever. She would give me one like every 4 to 6 hours and stuff. And I used to I liked the feeling so much that I used to save them. And then I would like take them like 2 at a time or something like that when I got my wisdom teeth pulled. And then like I only got the top ones pulled, so then I would get them pulled again, the bottom ones, so that I could get more pain pills because I really like the feeling.
Okay, so there's a caveat. All right, we're going to talk to Katie. I'm going to introduce you to Katie again at the end. But let's see what's going on in the brain. What part of the brain is affected? And so I like to call it the lizard brain. Every sentient being on this planet has this part of the brain. It's been in its current form on this planet for 200,000 years. It's the reward center of our brain. It's the part of the brain that tells you every day to get out of bed, find food, and find clean water. You might have thought your job was something else today, like to get out of bed and do some laundry, do your homework, get to school. But your only job, really, from an evolutionary standpoint, is to survive long enough to spread your genetic material to another generation of Homo sapiens to inhabit this planet. That's it. The problem is it's this very survival part of the brain, am I going to live or am I going to die part of the brain, that gets hooked in with drugs. if drugs landed anywhere else in your visual cortex where you lost your peripheral vision, or your auditory system where you may have lost the ability to hear high-pitched sounds, be really easy to fix. But it lands in this very primitive part of the brain, and it's hardwired. So let's walk into this interaction that's going on in this reward center. Okay, so it's the dopamine pathway. And if you haven't heard the word dopamine, you're going to be hearing it the entire period today. But you do know the word, but you just know it by a different name. Dope. That's dope. You know, that's great. Right? Dopamine is made in the ventral tegmental area of the brain, and there is no quiz at the end of this, so I don't want you guys to feel daunted. And it's sent to the nucleus accumbens, and when that happens, it makes you feel awesome. It gives you incredible feelings of joy and euphoria. And it gives you motivation and drive to continue to do those behaviors. Okay? There are two main behaviors associated with this pathway. They are compulsion. I do it over and over and over and over again, and perseveration or obsession. I cannot stop thinking about it. I think about it all the time. Think about those two behaviors when it came to your ancestors getting food, for example. They had to be really good at those two behaviors. They had to be compulsive about getting food. They had to perseverate. They thought about it every night before they went to bed. How am I going to feed my brood in the morning? And in the morning when they woke up, how am I going to feed my brood today? And they were very, very good at those behaviors, and that's why they survived. That's why you get to be here, because they were really good at those behaviors. But think about somebody you know that's trying to quit smoking or any other substance that you might know of. They can't stop thinking about it. They think about it all the time, and they're supposed to think about it all the time. That part of the brain is working very, very well. So while these behaviors were really important for you to be able to be here and your ancestors to survive, they also help to destroy your life. So I want to talk to you about the relevance of dopamine to your particular life every day, okay? We assign a level of, before we do that, prefrontal cortex up here, part of your brain that's not fully cooked until you're about 24. Okay, so there's a lot of stuff going on in that. We're not going to talk a whole lot about that, but I want to mention that we will touch on it for a moment. Okay, so let's talk about dopamine as it relates to our lives. We don't take a blood serum test to analyze how much dopamine we have. We do this through brain scans. So we assign a level of dopamine to all of us, an average level of 100. We all sit at about 100. I put this up here because I think maybe genetically I got lucky, and maybe I have a little more dopamine. Maybe I sit at 105. So I wake up very motivated every day despite a lot of tragedy, but it's a genetic thing. So I might sit at 105, but we also know the Eeyores of the world, the people who, I'm never going to pass that test, I'm never going to make that team, you know, those friends, they're never going to like me. Those people, the Eeyores of the world, sit at about 85. If we're all at 100, they sit at 85. And we know these people, sometimes they're in our family. They just didn't get a genetic jackpot when it came to that. And it sucks to be at 85, okay? But if we all sit at 100, this is how dopamine works. If we all have a baseline of dopamine of 100 and you get your perfect food item, and I chose a strawberry because my daughter had me put in some strawberries and they were delicious and I was eating them when I was making this chart. But it could be an In-N-Out burger, Chipotle, whatever your favorite food, chocolate cake, all right? But if you get your perfect food item, you're gonna go from 100, you're gonna spike to 150, and then you're gonna come back down to baseline. And you spike because you're supposed to spike. That creates a very powerful memory in your brain because you need to remember, I need to, fresh strawberry, clean water, I need to remember this patch so I can return here, survive, and feed my young. That's why you spike in dopamine. You create a powerful memory. You don't get to choose whether you create that memory. It is made without your consent because this is the survival part of the brain. If you got to override your survival part of the brain, you would die. So you don't override this. Now, it's like this. If you got plunked down on a jungle floor, you need your brain to learn immediately when it's exposed to something that is going to give you nutrition. So you see a banana on the floor, and you pick it up, it's yellow, it's smooth, it's creamy, it's sweet. You're gonna make a very powerful memory around that banana. Why? Because next time you're in this place, like a jungle, this foreign kind of place, your brain has remembered. When you see a banana but it's in a tree, you're going to now have the drive and motivation to climb that tree, get the banana, peel the banana so that you can consume the banana. And if you are unable to do this, you won't survive. So that is why the brain gives you these spikes in dopamine around the survival behaviors. But we also have other behaviors in life. If we go back to our perfect food where we get to 150, but we do other things in life that raise our dopamine every day because they make us feel good. So what I'd like to do is ask you guys to think of some activities that you might do that raise your dopamine every day or once a week or whatever. Yeah? Playing video games, it does. It raises your dopamine. Yes? What? Oh, running, yes. Exercise definitely raises your dopamine, yes?
Finishing your homework just in time.
Finishing your homework, achieving something, yes. Yes. What is it?
Video games.
Oh, is that a video game? Okay. Okay, but listening to music can raise your dopamine, all right? Yoga, quest activities where you set a goal, like I'm going to climb to the top of a mountain, and then you get there and it's a release of dopamine. So we do a lot of things. Listening to music, dancing, singing, things that elevate your dopamine. And I'm going to give you guys a challenge to keep a to-do list for your whole life. You put one out every morning or make one every night before you go to bed, because checking off those boxes is a dopamine rush. And guess what? You're not doing anything that you wouldn't have already done. And so you might as well get a free dopamine ride from doing that. So those are dopamine producing activities we do that they help us feel good. So now I want to show you a few things that also will increase your dopamine. All right, I said great food is 150. Marijuana and nicotine or vapes will get you somewhere around 250, 300. Cocaine will bring you to 350. Prescription opioids will bring you to 500. Heroin, 900. Methamphetamine will get you between 11 and 1200. And wow, my gosh, wouldn't that just create world peace? Why would anybody tell you, after everything I said about dopamine, why would anybody try to discourage you from doing this? I haven't given you enough information yet, but yes?
Well, one would probably smell bad.
Go ahead, I'm sorry.
And two, it would fry your brain.
What was the second thing?
It would fry your brain.
Okay, we're going to talk about what it does to your brain, because frying your brain is just a colloquialism that we use, and who knows what that means in here? Yeah?
So you showed it the strawberry graph. The dopamine went up, but then it went down.
Yeah.
So if you take meth and you go up to 1,200, you're gonna go all the way down.
Eventually you do, and we're going to talk about why that happens. So let's look at that brain part that I showed you before, this interaction right here, where dopamine is made and dopamine is received. Okay? So it's this simple. Dopamine is made, dopamine is received, boom. Joy, motivation. Do that again. Dopamine is made, dopamine is received, joy, and drive to do it again. That's how easy that is. That's this pathway. Dopamine is made, dopamine is received. Now let's go inside the brain. We're going to look at that interaction between the two neurons where this occurs. Neurons are just cells that are in your nervous system, so we call them neurons. So here's the top cell. All right, it's making dopamine. The top cell is making dopamine, and I show it again as little baseballs. The bottom cell can receive dopamine. It's got little receptors to receive dopamine. So far these are the players. I will take your question after I finish this part. These are the players. How much dopamine we make, and how many receptors we have to receive this dopamine that sends an electrical pulse down that neuron, giving you these feelings of joy. and giving you that motivation and drive. So 2 players, how much dopamine we're making, and how many receptors we have to receive the dopamine. There is one more player. There's 3 players in this. We have little vacuums that suck the dopamine back out of the channel. So 3 players. How much dopamine we make, how many receptors we have to receive the dopamine, and how many and how efficient are vacuums. Okay? So I'm going to go outside the brain just for a second so that you guys can see a system that's more relatable perhaps. A post office. Our brain makes dopamine. Post office generates mail. The mail needs to be sent to the recipients, just like dopamine is sent to the receptors. So the mail is sent to the recipients, and any extra mail that either wasn't delivered because it's misaddressed or the people moved gets sucked back into the post office. So let's go back to the cell again and take a look one more time. Dopamine is made. How much dopamine we make, how many receptors we have to receive the dopamine, and then how many vacuums we have and how efficient they are to suck the dopamine back out. 3 players in this dopamine system. So now when we go back to this graph and we ask that question, we need another piece of information to answer the question why we wouldn't want to do this. Because we need to know, well, how are these affecting that pathway? What are they doing? And every single substance of abuse ends up in the dopamine pathway. They don't all start there. In fact, I'll give you one that does. But they start someplace else, and through lots of feedback loops, they wind up in the dopamine pathway. By definition, that's what a substance of abuse does. So let's take a look, and I'm not going to go through all the drugs and the mechanisms for them, but let's look at cocaine. Cocaine is really straightforward because it comes and it lands right in this pathway right here. It comes in and it blocks these little vacuums. So while the cell is still making a normal amount of dopamine, the vacuums are clogged and it can't suck the extra dopamine out of the cleft. So it sits in this cleft and it keeps pounding on these receptors over and over and over again. And that's how cocaine will bring your dopamine levels up to about 350. Okay? So now opioids, I have to wait for that to stop before it'll shift. Okay, opioids act on an opioid receptor on a different neuron, which then through a negative feedback loop affects the neuron that is going to release the dopamine, and actually what it does is it just throws out dopamine everywhere. So while the little vacuums are still working with opioids and heroin, they aren't efficient enough to get that dopamine out of the channel, and that's how prescription opioids will bring you to 500, heroin to 900. Methamphetamine does both. It blocks the vacuum and causes a more release of dopamine. Although I say that, but it actually does it does one thing more. It not only blocks the vacuums, but it actually reverses the vacuums. So instead of the vacuums sucking out the dopamine, it vomits it back into the cleft. So you just have all this cell making more dopamine and not sucking any out, but sending more through the vacuums. So that's how methamphetamine gets you to about 11 or 1200. Okay? So now we've seen the 3 players. We've seen how drugs can manipulate the pathway, either through causing more dopamine to be made or clogging vacuums, and that you can even have receptors manipulated where it increases receptor activity. So now when we look at this, I'm going to give you a hint why we wouldn't want to do this. I said it earlier. This part of the brain is 200,000 years old, and it knows a normal dopamine signal. So why wouldn't we want to do this? What could happen? Yeah.
Well, I mean, once the drug stops working, it could put you in like a depressed state.
And there's a reason. Okay, because he said once the drug stops working, it can put you in a depressed state. So let's take a look at what happens. When the brain sees levels of dopamine, it's used to these levels, right? And it's 200,000 years on the planet, it's used to 150, even 200 with different activities. But when it sees levels of, 275, 355, 900, and 1,000, it says, holy crap, in my 200,000 years on this planet, I have never seen dopamine like this. Something is terribly wrong with my brain. I need to turn the volume down. Now, we saw the 3 players. How much dopamine we're making, how many receptors we have to receive the dopamine, and how many vacuums we have to suck the dopamine back out of the cleft. So when the brain sees dopamine like this, it's going to turn on every vacuum in sight to suck that dopamine out of the cleft. It is going to burn up 80% of its receptors, and it's going to stop making dopamine. 3 things it has at its disposal, and this brain is going to do all 3. 1, 2, or all 3 combination. Okay, so what's the problem with that now? Let's take a look again at the healthy brain. The healthy brain has a baseline of 100. You get your perfect food item, 150, come back down to baseline. Now, all addictions occur differently, not only because different substances of abuse act differently and have different mechanisms, but also because each of your brains is individual. So I'm going to take a very straightforward addiction like heroin or opioids because it happens very quickly. But this is how addiction works. You start at a baseline of 100, and you'll get your first drug high, say at 900, if we're talking about heroin. You will never get there again. Even 2 hours later, if you go to try to get high again like that, you might get to 880. You won't get to 900. We call that chasing the high. The brain has already started to make some adjustments. And then it's going to make another adjustment, and you're going to administer again. God, I just want that feeling one more time, and it'll make another adjustment. And if the only thing we have to worry about is that, what's your name? Wayne? William. If all we had to worry about is William, poor William, why does he keep trying to get high? That's sorry, we're throwing you under the bus, but no, if all we had to worry about is, gosh, look at William, he's just trying to get high. No. What happens with William after repeated administration of a substance is that when William wakes up in the morning, William is not at baseline at 100 eventually. William's baseline bottoms out. And when William wakes up, he's at 30 or 35. It's hard to function when your dopamine levels are 35. It's hard to get out of bed. It's hard to pour a bowl of cereal when your dopamine levels are 35. We talked about a to-do list. William won't even be able to get over to get a pencil to make a to-do list. His brain feels awful, and there is absolutely nothing that is going to bring his dopamine levels back up, except one thing, and you guys can all guess what that is: the drug. And so William goes back to the drug, not to get high. William goes back to the drug because it's the only thing that's going to raise his dopamine, and he'll be happy if he can push through a day at 85. An Eeyore kind of a day would make his day. And that's why he keeps going back. And that's what we call the broken brain. It's a messaging system in our body like everything else. Every chronic disease is a disruption in a messaging system. Diabetes. Our pancreas stops making insulin. Disruption in the messaging system. Addiction. Brain stops making dopamine. Diabetes 2, which is adult onset, early adult onset, from poor diet and exercise. You burn out your insulin receptor. Addiction, you burn out your dopamine receptor. Every single chronic disease works this way. So what I want to do is tell you that something about addiction, and I'll take your question just in a moment. Addiction, it's the most prevalent disease in America. So if you're going to worry about any disease at all that you could develop, addiction is number 1 on your list because it is the most prevalent. So if you worry about cancer or something else, this should be top on your list. It's the number 1 cause of death. Okay, so if you're worried about getting something, again, the disease of addiction is one you don't want to get. It's the number 1 prevalent disease, and it's the number 1 cause of death. Guess what, though? It's also almost 100% preventable. Okay, but you only have a very small window of time in order to achieve that. It is a pediatric developmental brain disease. And I know that's kind of a mouthful, pediatric, you know, pediatrician, child doctor. So it's a pediatric developmental brain disease. 90% of addictions start in the teen years. It doesn't mean that, you know, 13-year-olds are shooting heroin, although some are. But it means that you are programming your brain right now for developing the disease of addiction. Okay. Okay, so I want to talk about the risk factors for developing the disease of addiction. And there are 3: your genetics, early use, and early childhood trauma. And I'm not going to talk about childhood trauma except to say that there are bad things that happen in a lot of our homes, and we grow up thinking they're normal, and then at some point we question. And if that's you, just find an adult to confide in, because that's really important. So we're going to talk, though, about genetics and early use. Your genetics are 50% of your risk of developing addiction. That means if you have a parent or a grandparent who suffers from addiction of anything, any substance at all, your chances of developing the disease yourself is 50%. Now, why am I telling you this? So that you can go home and feel bad that, oh God, I'm destined? No, because you have a window of time to change that. You can actually erase your genetics practically if you do the next thing right, but you have to do it right at a particular time in your life, because otherwise it's too late. So I'm going to give you this graph. This alcohol was used in this study, but this study has been done with numerous substances, and the trend is the same. The numbers are a little different because different substances of abuse have different addiction potential, but they all have the same trend that we're going to see. So alcohol in this study was defined as 2 drinks a week, not a day, a week. And a drink is a 5-ounce glass of wine, 1 shot of liquor, or 1 beer. It's not, 3 shots of tequila in 1 beer. That would be 4 drinks. Okay, so this is 2 drinks a week. So if you start drinking at 15 like that, 2 drinks a week, the chances of you becoming an alcoholic are 40%. If, on the other hand, you wait until you're 21, your chances go down to 7%. That's a precipitous drop. And so we want to look at the science. I'm giving you the data, but now we're going to talk about the science. What is going on in this brain during this period of time that causes this huge difference that we see in your potential to becoming an alcoholic or any use of any substance, it turns out? So this is that same graph, and I just put it up here to show you that the graph I just showed you is in blue. The red is if you have a genetic vulnerability to it, and the black is if you don't. So if you do, you're even higher than 40%, and if you don't, you're lower, but that's kind of the total. And look at in any case, if you wait until you're older, your risk for the addiction goes way, way down. So what's going on in the brain? I like to look at it as we're making order out of chaos. Your brain right now has tens of billions of connections, and nobody needs that many. In fact, you'll have a very unhealthy brain if you keep all those connections. You've made them because now is the time when your brain is discerning which ones it needs to keep. You're testing your environment, and you want to make sure you have the capacity to handle things. And so the first thing, though, it's doing is it's pruning back some of these connections. We call it synaptic refinement. It's pruning back some of these connections it doesn't need. And at some moments in your life right now, it's happening at 30,000 a second. A second, like boom, just now you lost 30,000. You don't know when you're losing 30,000, but it's happening all the time in your development right now. That's right. That's one of the things your brains are all doing right now, is synaptic refinement. It's pulling back some of these connections that it doesn't need. The other thing it's doing It's myelinating or insulating the ones that it does need. So it's getting rid of the old dusty roads and it's making highways. Okay, so think about it. If you want to go downtown, you want to get there in 25 minutes or 30 minutes. You're going to hop on the freeway. You don't want to be like a rat in a maze going up one street, down another, through a dead end, and taking 12 hours to get there. So you want the efficient pathways in place. So those are the two things, and I will talk about one more that your brain is doing. But first I want to mention that this is normal teen development, teen brain development. Your teen brain is supposed to be as crazy as it is. It's physical activity seeking, sensation seeking. It's act now, think later. You have less concern for negative consequences to your behavior. You have less than optimal planning. You feel emotions very intensely. And in fact, there's never a time in your life that you will feel emotions with such a large spectrum as you do in your teen years. You act first, think later, and you're strongly influenced by your friends and peers, and you're supposed to be. Because, 2,000 years ago, when you were 17, you were kicked out of the cave. You were another mouth to feed. So you had to find your herd. And I want you to pause and think about that for a moment. When you were 7 years old and you're on the playground, and your friend says, let's do this really stupid thing, you're like, that's kind of stupid, I'm going to tell the teacher. And when you're 27, your friend is going to say, dude, that's just stupid, I'm not doing it. But at 15, 16, 17, you're like, dude, I'm all in. Let's go see what happens when we do this really stupid thing. And that's a brain desperately trying to find its people, trying to find its herd. So it isn't a faulty brain. It's doing exactly what it's supposed to be doing, which is why we need very healthy activities for you guys to reach out to. One other thing, and this is going to bring this full circle, that your brains are doing right now, is they're laying the receptors in, the final receptors in the outer cortex of your brain. And one of those receptors is our friend, the dopamine receptor. So now I want to ask you guys a question. And this is, you have a 50% chance of getting this one right, so think about it. If at a time when your brain is trying to figure out how many dopamine receptors to lay down, if you are indulging in substances of abuse which are causing more dopamine than normal to be made, what do you think the brain is going to decide to do when it's programming how many dopamine receptors it's setting down? Yes?
It's going to create more than you should have.
It's going to do what?
It's going to create more than you should have.
No, if that happened, no. It actually is exactly opposite. Because listen, the brain is 200,000 years old. It's saying, wow, this is a lot of signal. They don't need so many of me because I've got so much dopamine here. I want to reduce the signal to what I know is more normal. Does that make sense? Yeah, I could see why you would say more, because it's like, oh, I got more to accommodate. I better make more. But what we see in scans is that we actually see a reduction in the number of dopamine D2 receptors in brains of people who suffer from a substance use disorder. Yes?
What would happen to a person if, well, I have two questions, but what would happen to a person if their dopamine and their dopamine receivers just completely got cut off?
A rat without dopamine D2 receptors will die of starvation next to a full bowl of food. So you would die.
And
Okay.
also, what if dopamine causes you to feel happiness and without dopamine you feel sad? What causes anger?
That's a different, that we're talking about emotion, and dopamine isn't the only thing that makes you feel good. Serotonin does too, and that's like for mood, more than mood and memory, versus dopamine, which is in the survival pathway. Anger isn't associated with dopamine that way, it's an emotion. And so I'm not sure how I would answer your question from a scientific standpoint. I think some of it's learned behavior, mismanagement, and I imagine that if you're coping all the time with substances of abuse, you might not be able to have functional relationships and could bring out anger. So that's more of an emotional thing. So I can't really answer that question. I said this was gonna be the third thing. I know the brain kind of holds three things easily, but I'm gonna give you a fourth thing because another thing the brain is doing is it's laying down, it's not laying down the neurons, it's programming your dopamine producing neurons. How much dopamine should I be making? So again, I'm gonna ask you this question. If at a time when the dopamine producing neurons are deciding how much dopamine they should be programmed to make given any activity you're doing, if you're artificially having more dopamine than you normally would from your normal reinforcers, what do you think it's going to decide to do? Anybody? It's going to make less dopamine. Why? Because it already says, this is a lot of dopamine. I don't need to make so much. So they'll shrivel up. And you know what they do sometimes? Is when your brain isn't using, or when your body's not using cells, they undergo apoptosis, which is cell death. And neurons aren't mitotically dividing cells. They don't grow back. So think about this now. You have fewer receptors. You have less dopamine you're making. You're vaping all the time now or whatever, and finally in college you stop vaping and you start doing other things and you're productive, and then, at some time in your life you start going shooting pool with your buds and you're, having beer, and your brain says, whoa, have another beer please, because that's what you promised me. That is what I'm wired for. And this isn't about whether it's alcohol, whether it's marijuana, whether it's about any other substance, because what the brain is craving is dopamine. That's why you could be vaping now, but you become, using heroin later. I mean, I'm using heroin, but you could, it could be cigarettes, it could be anything. And when you go to AA meetings, one thing you see almost 99.9% of the people doing is smoking and drinking coffee, because addictions transfer. So you've primed your brain and programmed your brain for addiction, and that's how it happens. And so I do want to spend a moment talking about vaping, because vaping lands in this dopamine pathway, and this is the pathway that I've been talking about in terms of addiction. But there's one other thing in vapes that how many people in here say, oh, vapes are, vaping is just vaporized water. It's just water. It's so much better for you than cigarettes. How many people have heard that? Yeah. How many people think that it's just water? Right, because you wouldn't be spending $15 on these puppies if it was just water, right? I don't know how much they actually cost. But no, so I want to talk to you about one thing that's also in these, okay? It's called propylene glycol. It's completely safe. It's FDA approved, but it's safe food grade. But you're not eating it when you're vaping it. You're combusting it. And when you combust propylene glycol, it turns into formaldehyde. Who knows what formaldehyde is used for? Anybody?
Preserving dead stuff.
Preserving dead stuff. Preserving things. And we use it in molecular biology to fix cells so we can look at them under the microscope. So how does that work? And I don't know why there's a buzzing noise in this, but here's a lipid membrane. Your cells all have lipid membranes around them, and all your organelles inside your cells have lipid membranes. They are very, very fluid. And these proteins sit inside these lipid membranes, and they're meant to be very fluid. But what formaldehyde does is it comes in and it binds to some subgroups on the proteins, and then they cross-link to each other, which causes a very rigid structure. And that's what's in the vapes as well. So I just want to make sure you all understand, while it's FDA approved and food grade, it is not meant to be combusted because it converts. And that's why marijuana, when you smoke marijuana, it has to be combusted, or they put it in food, they cook it. It has to be combusted in order to get the active ingredient. Well, that happens with a lot of things, and it happens in this case that formaldehyde gets made. So you're not just vaping, water, you're getting formaldehyde, and other things, but I wanted you just to see one example. But really my focus has been today on this, addiction. It is the number one cause of death. It's the number one disease you're likely to get. And yet it's pretty much preventable for every one of you. But you have this very small window of time to do it. Now, I'm going to go back to Katie because I want to give you a little history on Katie. Katie got in a bad car accident right after she graduated high school. She broke her neck. We already saw her desire for, she already knew she liked these pain meds, and now she was prescribed a whole lot of them for a whole long time. And at one point she got switched doctors because she went out of town, she moved out of town and then missed some appointments and she lost her prescription. They wouldn't re-prescribe. And so she started buying them on the street, and then ultimately they were very expensive, and somebody said, try heroin, it's so much cheaper and it does a whole lot more. And so I want to describe the symptoms of this kind of addiction. The symptoms of addiction are behavioral changes so devastating that even under the most severe threat of punishment, you cannot stop taking the substance. Jail threats, you lose your job, you lose your family, things that you really care about. You can't stop. And those are that's the symptom of addiction. And Katie's going to describe how it feels.
I would lie to my friends, so that I could go and do it. And, I would try and get them to lie for me, stuff like that. And I'm not even that kind of a person. To where, I would lie like that, and it just turned me into some, monster. It was that was the first thing I thought of in the morning, and I was if you don't go and get me, a fix, I'm gonna lose it, because it was I would go crazy if I didn't have it. So, I would literally do anything, I used to sell all my stuff. I've sold thousands of dollars worth of things that, were valuable to me, just so I could go and, get a bag. It was stupid. And I've talked to people that I don't even know. I've driven people around that I don't even know that could have killed me, just so I could get a fix. I was homeless. I didn't pay my bills just so I could, buy heroin instead. Every single paycheck, I spent it all the first days on heroin or pain medicine. So, yeah, that happened for a while.
That's Katie, and Katie's 25 now. And I want to remind you that this disease is a chronic disease, and it's treatable, not curable. It's preventable, but only as a teen. Once you develop the disease, it's a lifetime condition. Katie will always live with this condition. She's been taking medication for it, but even that, we relapse. Just like every other chronic disease, we have relapse rates. It's a very difficult disease to treat because we don't have doctors who learn about addiction in medical school. They don't teach it there. And we don't treat it like a normal disease either. When we find somebody goes into treatment and they get better, what we do is we stop the treatment. We say, oh, you're better. And then when the person relapses, we say, oh, the treatment didn't work. No, it worked. You stop the treatment, and we do not have a medical system that keeps ongoing treatment. So it's not a disease that you want to get because it's the #1 killer, and we do not treat it medically. Okay, so I want to go back to this one more time because I want to drive home the point that just because you go out and drink and you're safe and the next morning you woke up and you were able to get your work done, you say, see, I'm fine, my brain's fine. No, you don't know what happened to your brain. You were safe that day. But the programming that's going on in your brain, because of all the developmental changes that are going on in your brain and what you're affecting, you have no idea what you've done. That night, you're safe the next morning. But you did not protect your brain. So I want to drive one more point home. I want to tell you again, if at 15 your chances are 40%, if you could just take this window of time till you're 18, like out of high school, your chances go down to 12 or 13%. It would be great if at 18 you might say, I'm gonna keep doing it, I'm gonna protect my brain. Why? Because the quality of the next 70 years of your life depends on the decisions that you make right now. And I mentioned that your prefrontal cortexes are not fully developed. So it's very difficult to imagine that I am standing here saying, protect your brain, even though you're impulsive, you take risks. That's what your brains are supposed to do. And that's why I don't come up here and give the sermon, just say no, because it doesn't give meaning. But hopefully understanding the science, what is going on in your brain neurobiologically when you indulge in substance use, hopefully understanding that will help you make a better decision that will have meaning over the quality of the rest of your life. And so Another thing I want to mention is that the prefrontal cortex that I did mention before, that's not fully developed, is also highly dependent on dopamine. And so when you deprive that part of the brain of dopamine, you have decreased activity. And that's the part of your brain that's your brakes. That's the part that allows you, if you are driving down the street and you don't have brakes in your car, and you see a person crossing the street, it doesn't matter how hard you press that brake, that car is not going to stop. And so when you think about your prefrontal cortex needing to be healthy for you to make good decisions, is dependent upon what you do right now. It's the part of the brain that measures satiation. If I'm hungry, food is very rewarding, but if I'm not hungry, is food rewarding? No, but that's the prefrontal cortex that shifts. It helps make that shift. And when that's damaged, you can't do that, whether it's overeating or any other substance of abuse. So I didn't know how long it would take me to get through this. So I do have a couple slides on marijuana if somebody's interested. But I first want to open it up to some questions if people have questions about this. I just, again, to drive home, if you can just try to make commitment about delaying your use. And let me give you one more strategy, then I'm going to take questions. I want you guys to think about when you go to a party tonight or any other night, bring your own drink, not alcohol. Bring your own drink. You'll be less likely to be offered a drink. Practice in the mirror strategies for saying no, because you're wired to have peer pressure. It's important that you fit in with your friends. So have some oh no, dude, I can't because I gotta go. My mom wants to talk to me when I get home. She'll know if I'm high. Or, no, I gotta play soccer tomorrow. I've got a big game, so I can't do. Whatever excuse you're comfortable, practice it at home. Because you need to be comfortable saying no to your friends and not have them feel like you're judging them. Okay, so yes.
Well, I already know if this is physically possible. Probably isn't. But what would happen if your brain, despite our ancestors, kept producing more dopamine and more receivers, and it just didn't stop?
Yeah, so drugs don't only impact the dopamine pathway. They wreak havoc elsewhere. But I want to drive home that that is the important part for your brain development right now. And you have this window of opportunity to make a difference in your own lives. So are there any other questions? Are we out of time? I have trouble seeing the clock back there.